Hello everyone and welcome back to the lecture again. So in the last class we have talked about the synthesis of the nucleobases. In the last lecture we have talked about the synthesis of the purine nucleobases which has two rings, that is one 6-membered ring fused with a 5-membered ring, and we have seen how the synthetic methodologies can be used to produce these compounds industrially as well as in the for the laboratory use. At the same time, we have also talked about few experiments to understand prebiotic chemistry, how these molecules, such kind of molecules would have been synthesized millions and millions of years ago on Earth, where there was when there was no biological molecules, when there was no life. So the prebiotic chemistry, when we have talked about, the experiments are basically the hypothesis or the postulates actually which tried to understand the mechanism of synthesis of the larger molecules out of the smaller molecules that were likely to be present in that prebiotic earth. Prebiotic earth means I am talking about the primordial soup which had the basic compounds or the elements, the basic compounds and the gaseous compounds, for example methane, carbon monoxide, carbon dioxide, water, ammonia and all sorts of the smaller molecules. And of course there was very less amount of oxygen, so it is kindly anaerobic condition. One thing is, of course, we have to keep all the time in mind is that that has been happening millions and millions of years. They were there in that soup, and the environment was quite drastic that time. It was very high temperature, and then a lot of electric spark used to be there. So the very drastic conditions. Now when you look at the experiments that try to mimic those prebiotic earth, are actually cannot be mimicked in exact type, because of mainly of course two reasons. First reason is the time that the reaction was happening on the prebiotic earth. The reaction was happening since millions, sometimes billions of years time frame, and that much time you cannot provide when you are doing the same thing in the laboratory. So that is one issue. Second one, the temperature and pressure very much you can create in the laboratory. You can recreate the similar kind of conditions in the laboratory, but time is one thing that you cannot recreate. And second is of course the degrees of freedom. The earth was very much open, so the molecules were floating all around, very high degrees of freedom for the molecules, and the liquid that was there, we call it primordial earth or primordial soup. And when you do the same thing in the laboratory in a small container, your degrees of freedom are really restricted. So the molecules cannot float around or cannot roam around as much as they used to be in the beginning of the earth. So these two are the issues that are associated in mimicking the primordial reactions or the prebiotic reactions in the laboratory. But so whatever I have shown here are basically the hypothesis that which suggests that the synthesis of the nucleobases particularly may have happened in the same fashion. The mechanism could have gone through the way that we have seen. Okay. So today, so I have covered the synthesis of the nucleobases, both pyrimidines and the purine nucleobases. So the next thing is the nucleosides. So nucleobases are complete. Now, so we are trying to go up to the synthesis of the nucleic acids, so which means DNA, the full synthesis of DNA or the full synthesis of RNA. So we have seen how the nucleobases can be synthesized in the laboratory. Now comes the nucleosides. So nucleosides basically means the sugar plus the nucleobase So, this has been done. Now, we have to see how you can attach the nucleobase with the sugar. So, your target molecule is something like this. Here is the nucleobase, can be adenine, can be guanine, can be thymine, can be cytosine for DNA, or can be uracil for RNA. And when we are talking about DNA, then this is the sugar chemistry or sugar conformation. This is the for the DNA nucleoside. If we talk about RNA, then your target would be here nucleobase, there will be hydroxyl here, this would be your target. So, first we will start with the RNA one, because this is more general, this has the hydroxyl group present here also, then we will go specifically to the DNA. So, here what is the target is, you already have synthesized nucleobase. So, your target is how to connect the nucleobase with the sugar moiety at this position. If you do look at the numbering, this is called the C1 prime or 1, simply if you can write 1 prime position. So, nucleobase, connection of nucleobase at the 1 prime position of the sugar, that is your prime target now. So, there can be lot of alternative methods, I will show you that in this slide you can see. So, there can be other ways also to synthesize the nucleobase with the sugar attaching at the 1 prime position. First one is of course, as I have talked about, this is your nucleobase that you can attach, the whole thing you can attach to the C1 prime of the sugar, and of course, it will be kind of a nucleophilic substitution reaction. So, therefore, in the sugar moiety you need to have a good leaving group, so that the nitrogen on the nucleobase can attack as a nucleophile and eliminate that. So, you can have this compound, your target molecule, that is pathway B, and this is what we will mostly follow in this. There can be other ways also. One is so B and C, pathway B and C both involve that you are synthesizing the nucleobase on top of the sugar. So, in this case nucleobase was synthesized separately, sugar was synthesized separately, and then they were coupled together. But here you can see that using this you are synthesizing the whole of the nucleobase on top of the sugar. So, with amine free, again two ways, one is keeping the 6-membered ring intact and forming the 5-membered ring here, or alternatively you start with the 5-membered ring on the sugar and synthesize the 6-membered ring. So, both of these ways are as we have seen before, but only thing difference is that you are synthesizing the whole molecules on the sugar. We do not use these methods much nowadays. Mostly people use this method where you synthesize the nucleobase separately, sugar separately, then couple them together. So, first kind of the synthesis was done by, it is a name reaction, Fischer Helferreich synthesis. This is one of the first kind of successful synthesis of the nucleosides, and for which Fischer is very famous actually for his synthesis of the purine, especially the purine nucleosides and nucleotides. And Fischer received Nobel Prize in long back 1957 for his famous purine synthesis protocols. So, in this case what they have done is, you have the sugar with a leaving group as I have said, and then You start with this with a leaving group here, and for example, you start with adenine, there is amine here, and you have this is what is your adenine, and you try to couple them together. Now, look at the problems here. So, what is your target? Your target is basically here, this is the N9 position of the adenine, which should react. So, this nitrogen basically should react this carbon, eliminating the bromide. So, this is your target. Now, what are the problems associated with this reaction? First one is of course that you have the other hydroxyl groups in free form, which can also react, which can participate in the reactions, giving you all the unwanted products, unwanted side materials. So, the first need is to protect these hydroxyl groups so that they do not react or they do not hamper into your desired reactions. So, first thing that they had to do is protection of the sugar. This sugar has been converted to protection means if you make the alcohol. So, these are basically, this is secondary alcohol, this is primary alcohol. If you convert the alcohols into the acetates, which is an ester basically, and ester are very less reactive because esters have internal resonance within themselves. So, their reactivity is pretty much less compared to the free alcohols. So, if you convert the alcohol to the ester, that will protect the alcohol from doing the reaction. Similarly, I am not writing the whole. So, this is AC, CH3CO is acyl group, which is usually termed as AC. So, this would be OAC, and you can convert this also with OAC. So, then you can protect the other functional groups which could participate in the reactions. Now, your target is only here, so that the bromine can be eliminated, fine. Now, on the other hand, you have the nucleobase. Here what problem could happen? See, your target is that N9 should react with the bromide. So, this is the nucleophilic center, which means in this case if you use this form exactly, then the lone pair of the nitrogen should act as the nucleophilic center and attack the C1 prime. Now, here if you see, you have an amine group also, which also has a lone pair of electrons, and this would be more reactive because this is secondary amine, and here the lone pair is very much is inside the ring. So, lone pair is very much involved in the aromaticity. On the other hand, this is a free amine form which is more reactive. So, if you leave this amine free, then you will get the most unwanted reaction, that this amine will react to the C1 prime. Hence, you need to protect the amine also first, and this can be done using NH amine can be also protected by acylation. In this case, a very good protecting group is this. You can use the simple acyl also, as we have seen for the other one. Here, this is one protecting group that is being used for the protection of the amine kind of functional groups. Here also the same thing. Once you do the protection, the lone pair of electrons on the amine is very much involved into its internal resonating structures. So, there are internal resonance, so that the lone pair of electrons is not available to do the reactions with other molecules. So, that is how the amine can be protected. So, you have to start with this sugar with the protected ones and with the protected version of the nucleobase. Now, if you mix them together, you try to do the reactions, you can pretty much expect to have nucleophilic substitutions between this and this, but still it does not work fine. The reason is, here you have OAC, here you have OAC, here you have OAC plus NH. I am not drawing the whole protection group, I am writing P. So, in this case, this I am terming as P for protection. So, NHP. Now, if you see the sugar chemistry is actually pretty hard to do, because the carbons are not very much reactive, they are not much electron deficient carbons. So, doing nucleophilic substitution is not very facile. Here you have, these are in these carbons, these are primary secondary alcohols, here you have primary alcohol. In this carbon, which is our target, heteroatom is attached there, but that does not make the carbon much electron deficient. If you have other electron withdrawing groups such as carbonyl and all these things, that would have made the carbon more electron deficient, number one. So, sugar in general are not very reactive. On the other hand, nucleobases are not reactive either much. Nucleobases are not very strong bases, so their nucleophilicity is less, and the lone pair of electrons, as I have told you earlier, they are involved in the internal resonating structure. So, it is a part of the aromatic system. So, they are not available much. Reactivity of the nucleobases is also less. Therefore, if you mix this and this together, then you are not going to get much of your product. So, the need is that you need to activate the reactivity on the nitrogen. So, that you do by one of the old method is that if you treat this with mercury chloride, then that takes away a proton here, leaves you with HgCl, and HCl would be eliminated, NHP, nitrogen, nitrogen. So, you have an HgCl bond. This is the new bond that has been formed. Now, why mercury chloride we have used, I will tell you. So, mercury has high electropositive, it's an electropositive element. So, it will try to remove the electron from there, it wants to be in the positive charge form. So, therefore, this bond is not really a covalent bond, it exists very much as a nitrogen minus and Hg plus, because mercury is stable as a cation, Hg plus form. You have started with Hg2 plus mercury chloride. So, this very much exists kind of an ionic bond, less a covalent bond, more of an ionic bond, or you can call it a kind of a salt. So, therefore, positive charge mostly restores on the mercury, and that leaves you with the negative charge distinctly on the nitrogen. So, now you have a good nucleophile with almost a free negative charge, and this is the reason that it wants to release away the electrons. So, now if you treat this molecule with the sugar, and typically they do it in an organic solvent xylene, 120 degrees Celsius temperature, that gives you the nucleophilic substitution here, and you have your target molecule. OAC, OAC, OAC. Here it mostly goes and here you have the NHP double bond, that is it, this compound. But you have to get back the free forms, deprotect it. This deprotection you can do by treating with ammonia in methanol. It will deprotect both of these, both the acetylate and here. This will leave you with free hydroxyl, free OH here, and here you will have the free adenine form. So, you have your adenine synthesized. Now, similarly, if you want to synthesize the guanine, for example, you start with this OAC protected OAC, this is also protected, plus you can start with the guanine, which is this, amine H, and here instead of H, of course, you have to use the HgCl, same treatment, xylene 120 degrees Celsius, and you can have your guanine. Of course, this is after. So, it is not only xylene, this is the fourth step. Second step is you have to deprotect everything else. That can be done by using the same way, ammonia in ethanol or methanol will give you the OH. All the OH would be coming here. There is another way actually to synthesize the guanine. Instead of using this, if you use, that gives a better result actually, that is why I am showing. Here, instead of using the free guanine, if you use this form, this derivative of guanine, I am sorry, here the NH2 requires a protection, the same protection of course, NHP. So, NHP, and you instead of using the keto form, you start with the chloride there and HgCl. Then what you get is this molecule here you have the Cl in NHP, here you have OAC, OAC, and here double bond here. Now, you have to get rid of the chloride. If you do the hydrolysis in sodium hydroxide, a little bit water, then that will replace you will have the nucleophilic substitution kind of thing here, you will have OH there. And once you have OH, of course, this is the enolate form. So, it will immediately go back to the keto form. So, this will go to the keto form in here you have NHP in here, double bond here, this. So, you have your guanine and then you can go for the deprotection. So, this is your guanine now. I will just briefly explain that. See, you have started here. If you look at the stereochemistry of the sugar C1 carbon, we have started with the arbitrary stereochemistry. It could have been the up the plane, it could be the down the plane. So, both cases does not matter what is the stereochemistry here, whether this is up the plane, whether the bromine is down the plane. For ribose sugars, you always get the nucleobase which comes up the plane. So, independent of the stereochemistry of this, you always get the nucleobase of the plane, which is your desired stereochemistry of the nucleoside. In the nucleoside, always your nucleobase comes off the plane of the sugar. This is the up the plane, this is down the plane. And that is the reason. I will just explain in a brief while why this happens. This has to do with the rule that is known as the Baker's rule. So, this is for the pyrimidine, adenine or guanine, that you can go this way. Now, if you think of the pyrimidines, thymine or cytosine, I will give an example of the thymine here. We see bromine. Now, the similar way you can use the thymine with the HgCl. This is your methyl, double bond O, H, double bond O. So, this will react, will give you the correct compound. Up the plane, it gives you the thymine. I am keeping these protection groups. You can use the same methods, ammonia methanol treatment, to get rid of the protections. When you use cytosines, cytosine has one amine group here. So, you need to protect the amine group first and then do this chemistry. Nowadays, what we do, we use an alternative method which is more facile, or which will give you better result, but the yield of the reactions are much higher, where instead of the HgCl, if you have the thymine, if you use the enolate form. So, your idea is that to increase the nucleophilicity on this nitrogen. NH. Now, if you treat this with a silyl compound TMS chloride, trimethyl silyl chloride, which is basically this methyl, 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 and this is silicon chloride, trimethyl silyl chloride. Silicon compounds are very, very, very useful for organic synthesis, and they have nowadays in modern organic reactions, their use is in plenty in numbers. So, what this will do is, silicon reacts very easily with oxygen, with a double bond, maybe single bond oxygen or double bond oxygen, does not matter, it gives you eliminated reaction. Same thing will happen here, and that will give you, since if this comes here, this has to go to make the saturation. So, it basically allows you O SiMe3. Similarly, this will also happen here, and this methyl. So, this is basically the enolate form of thymine. It's quite stable compound. Now then how can you do this chemistry? The chemistry is I am just writing Me3, not the structure again. You already know the structure, and this. So you have the sugar with the bromine, protected ones. Now if you use, it's very easy to break this kind of bond also. Silyl compounds are very easy to break also. Just a little bit treatment with water, or even better is if you have fluoride F minus in your solution. If you use a tiny bit of F minus, then that reacts with silyl. It breaks this bond back and it comes back here, which creates a negative charge that will immediately react. So this becomes a much better nucleophile when you treat this reaction mixture with a little bit of fluoride or even with water. Same thing will happen here, it will be dehydrogenated and it will be hydrolyzed, giving back the thymine. So you will get your thymine back here. OAC. So the enolate form of the pyrimidine nucleobases, you can do it with purines also. With purine nucleobases, for example thymine or cytosines, you can treat that with trimethyl silyl chloride, get this enolate form and then react it with the sugar, protected sugar. That will give you a very easy or the more amount of much facile synthesis of the nucleoside. So now the question is, the same thing you can do with the cytosine. When you look at the sugar, I have started with this bromide and of course all the protected ones. And this has of course come, the protected ones of course come from its original one with OH, bromine, and then OH here, OH there, OH there. So this can be converted into this as we have seen. Now how to get this CBr? So this you can actually get very easily if you start with all protected. For example, if you have the free form here, OH, and you randomly protect all of them, treat it with acetic anhydride. Acetic anhydride is now banned in India. So similarly you can treat it with acetic acid also, little bit high heat, reflux, then excess of this material, excess of the acetic acid or acetic anhydride, then everything will be protected. This will be OAC, this will be OAC, everything would become acetate because you have used not excel, excess. Now this if you use, treat it with tin bromide or tin chloride. If you use tin chloride, you are going to get chlorine here. If you are treating with the tin bromide, SnBr4, then you are going to get bromine here. So if you treat it with SnBr4, then you are going to get a reaction which will happen only here and it will give you Br. And the Br will mostly come at the beta position, the up the plane, Br here, OAC, OAC, OAC. The reaction goes this way. if you have Br4 is basically Br3 and Br10 is a kind of a Lewis acid. So, the lone pair of electrons will go there, eliminating Br minus, and this Br minus reacts here. So, ideally if the acetate is up the plane in the beta position, then as a nucleophilic substitution rule your Br minus should have come from the opposite side, but it does not happen. Independent, no matter what you use there, the stereochemistry here, be it beta, be it alpha, you always get a beta isomer of this compound, and this comes from the rule which is known as the Baker rule. This is what the Baker rule is. It basically states that if you use sugar compounds like this, it can have different the geometry. If it is arabinose, D-arabinose, I am not now talking in general sugar chemistry. D-arabinose will have the acetate. If you have acetate, this would be the 2' position would be up the plane, beta position. If this is a lixose, then 2 and 3 both are up the plane. If you have ribose, then both are down the plane, and we are using ribose. So, both are down the plane for our case. If you have xylose, then 2' is down the plane, 3' is up the plane, and this is the 4' is also down the plane. But in all cases, whatever stereochemistry you use of the C1', be it a beta, be it alpha, when you do the reaction, when you do a nucleophilic substitution reactions, their stereochemistry does not matter. What matters is what is the stereochemistry at the C2' position. If the 2' position is up the plane, 2' position is up the plane, then your nucleophilic substitutions, this can be a base, this can be any nucleophile. The nucleophile will come down the plane in the final product. So, if 2' position is up the plane, 2' position is up the plane, then the nucleophile at the C1' position will come opposite side of it, down the plane. So, in this case 2' position is, I am just writing OAC, up the plane, then the nucleophile will come down the plane, alpha anomer is going to be your major product. Similarly, here if your 2' position is down the plane, 2' position down the plane here, 2' position down the plane here, does not matter what is the stereochemistry of the other positions, not even the C1', then you will have the beta anomer, your nucleophile is going to come from the up the plane. So, that is what the Baker's rule is, that the stereochemistry when you are trying to do a reaction at the anomeric position, the C1' is known as the anomeric position. When you are trying to do the nucleophilic reaction or a substitution reaction at the anomeric position, then the stereochemistry of the final product will depend not on the anomeric atom or anomeric leaving group, but will depend what is the stereochemistry of the 2' position, and it is always the opposite of that geometry. If 2' position is up the plane or in beta position, then you are going to have the alpha anomer. If they are down the plane, you are going to have the beta anomer. So, there is a reason for this also. Why? So, same thing is happening here. If you look, if you come back, that it does not matter what is the stereochemistry of your OAC here, since this is ribose sugar we are using. So, a 2' position is down the plane. Since this is down the plane, your bromine or the chlorine or the nucleobase, if you do, is going to come from up the plane. The beta anomer is going to be your preferred conformations. Now, there is a reason for it also. Why is that? So, if you look, OAC. Here, since this is involved, I am going to draw this structure. So, always your 2' position is dictating what should be the stereochemistry at the 1'. Now, if you treat it with SN, Br4, Br3 and Br, then this is going out, which means you are going to have a transient intermediate OSE, and this is going to be your SN Br3, this is going to be your plus, and Br minus there, OAC, OAC. Now, since you have a positive charge here, it is going to leave, and immediately this is going to attack. The oxygen or the double bonded oxygen of the acetate is going to attack immediately to the C1' position, because you are having a positive charge here which is leaving. So, that is giving you an intermediate, which is this. Positive charge, OAC, OAC. This kind of intermediate is going to come. So, it is intramolecular nucleophilic substitution reaction, because the acetate group of the same molecule is attacking as a nucleophile. So, if you see here, the acetate group is attacking as a nucleophile, and this is your leaving group. So, internal nucleophilic reactions, or we call it NGP, neighboring group participation. Because of neighboring group participation, it forms this kind of intermediate. So, whole of the intermediate that would be forming is down the plane. Now, the Br minus that you had, from which side it will come? Your down the plane is blocked. So, only available position is up the plane. So, Br minus has to attack from up the plane, because down the plane is blocked by the intermediate formation, intramolecular intermediate formation. So, therefore, this is going to attack, and it's going to come back, because it's an intermediate, it's not very stable. You are going to get back your OAC, OAC here, and your bromine has to come from up the plane. So, beta anomer. So, that is what the Becker's rule basically states. So, similarly, when you are treating this with a thymine or any other nucleobase, if I use the OTMS, the silylated one, OTMS, then this is going to attack. Again the same thing will happen, Br minus will be eliminated, the OAC will attack from backside, it will create an intermediate in the down the plane. So, your thymine has to come from up the plane, will give you always thymine as the beta anomer. This is going to be your product. So, now that is for the sugars. So far we have taken is the ribose sugar. So, this is D and ribose sugar, right, for RNA molecules. Now, if you want to synthesize the DNA, what you have to start with? You have to start with the deoxyribose. For example, bromine here, nothing here, OH, OH, and of course, so this is for the deoxyribose. Deoxyribose sugar, we can start with the bromine version, bromide added, and of course you can convert it into OAC and do the rest of the reactions like thymine and adenine addition the same way. But here there is a problem. Now, if you start with any geometry here, you are not going to get the same beta anomer that we have seen for the ribose cases. The reason is, for ribose cases you had substitutions in this position which was down the plane, and that was dictating the stereochemistry of the incoming nucleophile. In this case, for the DNA case, you have nothing here. So, there is nothing to dictate the stereochemistry of the nucleophilic reaction over this position. So, if you want to get the desired beta anomer of the nucleoside, there is no other alternative but to start with a specific stereochemistry at the beginning. So, if you want to have the desired beta anomer, then you are going to start with the specific alpha anomer, alpha substituted bromine of this position, and then you treat it with the thymine. Just giving the example, OTMS, and this same conditions. Then you have little bit of fluoride or water, either of them you can use. Then it is going to be pure SN2 kind of reactions where your nucleophile will attack. Since this is down the plane, your nucleophile will attack on the opposite part, that is the up the plane. You are going to get the thymine up the plane, but only when you are starting with a specific stereochemistry in this position. If you start with a random geometry here, you are going to get a random geometry. So, you will get a mixture of alpha and the beta product. If you use this, then you are going to get beta plus alpha thymine. A mixture of these two, which is not desired. What you want is, you are looking for this beta that exists in DNA. Here also, most of the times, even if you start with the alpha anomer, it is restricting the stereochemistry. Here is little bit difficult. You still get a little, to some extent, mixture of the other isomer also, but mostly this. So, for DNA cases, keeping the stereochemistry intact is a challenge, and that you have to keep it in mind. So, that is how you can synthesize the nucleosides, which means the nucleobases plus the sugar for DNA as well as for RNA versions. The next step is, of course, how you can synthesize the whole the chain of the deoxyribose nucleic acid, or the DNA or the RNA. That we usually do it in a, there is a protocol for it. It is a little bit advanced chemistry that I will explain in the next lecture. That is called the phosphoramidite chemistry, or we even call it solid state phosphoramidite chemistry, that is usually done in a machine, in a DNA synthesizer we call. That I will explain in the next lecture. But before that, I would like to just mention a little bit of the sugar chemistry. So, since we are doing with the DNA and RNA, I will restrict myself to the ribose sugar. For DNA it will be deoxyribose. So, I am making it more general so that we can handle it. Now, the question is, we have seen in the entire synthesis that sometimes you need to protect these sometimes you need to protect this, or you are converting this into the bromide as a leaving group. Other times we are protecting the other ones. So selective protections and deprotections are very important for sugar chemistry. Now in this we will try to do how to selectively protect one individually of all these positions. So first is C1, and C1 is very easy because the reactivity of C1 is very different than that of the others. Why? If you remember how the cyclic form is coming from, this cyclic form is actually coming from the acyclic sugar, which is basically this. It has a CHO, aldehyde. The open chain form, this is the closed chain cyclic form. The open chain form is this. One, two, three. So this is the open chain form, which has the aldehyde group here, and of course carbonyl compounds are much more reactive because they have electron deficient carbons because of the carbonyl group. This is double bond O. So because of this electron withdrawing nature of this carbon is little bit more electron deficient. So therefore C1 position, this is a little bit more reactive compared to the other positions, and you can easily do chemistry here, keeping intact all the other ones. So here if you want to do, for example, if you want to protect this hydroxyl with an acetate, all you have to do is to treat it with acetic acid or acetic anhydride in a very mild condition, and you can use pretty much one equivalent. The others will not react under this condition. You will get iacetate here, keeping intact all others. When you use a drastic condition, little bit drastic condition of acetic anhydride or acetic acid and excess of that, then only you are going to get the all of these protections. Otherwise it is mostly the anomeric position, we call this anomeric position, the C1 position, this is going to be affected. Similarly, if you want to do it a bromide or a chloride, you just treat it with HCl or HBr and you are going to get the reactions only in the anomeric positions because of this aldehyde form, that this is more reactive. So this is C1 prime position is done. Now other position, this is an secondary alcohol, this is also an secondary alcohol. So the reactivity of 2 prime and 3 prime are almost similar. On the other hand, this alcohol is a primary alcohol at the 5 prime end, and this is less crowded. Number 1 is the primary alcohol. So this is sterically less crowded, these two are sterically more crowded. So again, doing chemistry of the 5 prime position is little bit easier than this 2 prime and 3 prime. Now if I want to do selective protection of the 5 prime end, all I have to do is, if you use a large bulky group as a nucleophile, in this case it will be electrophilic reaction, because your OH is going to act as a lone pair of electrons through its lone pair of electrons. These OH are going to act as a nucleophile when you do the protections. So your incoming group that you want to do the protection with should be large in size, so that can only go to the 5 prime position and not here, because these are crowded. So one such reaction is if you use phenyl ring, 3-phenyl, and a chloride. This is known as trityl chloride. We will use this molecule later also when we synthesize the solid phase DNA chemistry. So this is trityl chloride, which has 3 bulky phenyl groups, or instead of trityl group you can use it little bit better, that is called the O-methoxy trityl, a methoxy group at the para position here and a methoxy group at the para position here. Two of them have the methoxy group at the para position. This compound is known as DMT chloride, dimethoxy dimethoxy trityl chloride, trityl chloride. So, this is this molecule, and this exists as a very good cation also. So, when you use this such kind of bulky group, then this OH or this OH cannot react, because these two are sterically crowded. Only the 5 prime will react, and that will give you the protected 5 prime position. So, we have protected here with OAC, leaving it with OH here, leaving it with OH here. Here you had the OH, now you had DMT, which means this group. So, DMT is a good protection group specifically to the for the 5 prime position of the sugar. Thank you.